After discussing refraction at plane surfaces, we now move on to refraction at spherical surfaces. Now, when we talk of refraction at spherical surfaces, what we mean is the surface separating the two medium. Let's call this as medium A and this as medium B. The surface separating the two medium is spherical in nature. Now, in this topic, let's assume that we have a single refracting spherical surface. As in this case, we have two medium, medium A and medium B, and the surface which separates medium A from medium B is a spherical refracting surface. In this case, let's assume that we have a object at this point, and this object has an image at this point. Now, when we have a single refracting surface and we have two medium, medium A and medium B, the equation which relates the object distance u with the image distance v is given by 1 by u plus mu by v is equal to mu minus 1 divided by r. This formula can be proved using, of course, the principle of least time. So if you are really interested in finding this formula, either you can go by geometry or you can go by principle of least time. I give this you as a homework. You try proving this equation on your own. Now, what is mu? Mu, in this case, mu is equal to the mu of the refracted medium divided by mu of the incident medium. So in this case, it is actually mu B by mu A, where mu B is the absolute refractive index of medium B and mu A is the absolute refractive index of medium A. And what is R? R is the radius of curvature of this surface. This surface can be assumed to be a part of some sphere which has a radius R. So this is the formula which relates the object distance with the image distance in case of a single refracting surface which is spherical. The magnification produced in such a case is given by V by mu into U. So you need to remember this formula, and you need to remember the formula for magnification in case of a single refracting surface which is spherical. A special case to this could be, let's say, which you discussed sometime before in the last lecture, I guess, when you had a refracting surface which was plane. In that case, you can say that R is equal to infinity, which means here if you put, you will get 1 by u plus mu by v is equal to 0, or v as mu u. That means in case of a single refracting surface which is plane, if this is the object distance, the image distance is minus mu b. That means image is formed in which space? C. This is my medium A, this is my medium B. The refractive ray goes in this medium. So this is my virtual space, this is my real space. So that means the image is formed in my virtual space at a distance of mu b. In case when the refractive index is when the surface is a plane surface. Now this formula is applicable in case of thin lens, which we'll discuss now. So till now we were discussing single refracting surface which was spherical. Now in case of a thin lens like this is the object, this is the image. Here you see that there are two refracting surfaces which are spherical. Let's assume that this refracting surface has a radius of curvature of R1 and this has a radius of curvature of R2. Okay. Now let's say that this distance is U and this distance is V, and both the sides of the lens has the same medium A. The refractive index of medium, let's say this lens is made of medium B, so let's say mu B by mu A is given by mu. So my question is, what is V? What is the relation between VU, R1 and R2? I want you to use the formula which we had discussed some time before. That is the formula for single refracting surface which is spherical. So how you will proceed? See, this is the first refracting surface. So if I write the equation for this one, 1 by U plus mu by V is equal to mu minus 1 by R. This was the equation I had. So this, if I put U, what is my V? V is positive in this case, is equal to, let's say, what is V? V is the image formed by this refracting surface. Let's say it's V1. Let's call it Vi. So it's mu by Vi. This is equal to mu minus 1 by R1. Now if I take this refracting surface, the second one, what is U? Vi is formed here. The ray of light is traveling in this direction. If I have to move from the object to the refracting surface, I have to move in this direction. That means it's opposite, so my U is negative in this case. So it's minus Vi. Plus, what is the refractive index of the medium this with respect to this? It's 1 by mu, because refractive index of this medium mu A with respect to the second medium mu B is what? It's 1 by mu. So it's 1 by mu divided by final image which is V. This is equal to 1 by mu minus 1 divided by R. What is R now? You see that R is positive because for this surface, this is the real space, this is the virtual space. This is the real space, this is the virtual space. R2 lies in this space, so it's positive. Now if you add both these equations, what you will get? You will get 1 by U plus 1 by V, which is equal to mu minus 1, 1 by R1 minus 1 by R2. So you'll get this equation. So I got this equation. This equation is known as the lens maker's formula. Lens maker's formula. Now this one we also write as 1 by f, where f is the focal length of the lens.